Hey class, I wanted to make a help video for this last question on the workshop. There's an important couple assumptions that I want to make sure you all are aware that we're making in this problem. The main one is that we're assuming or ignoring really the rotational inertia of Gus's ball since we haven't learned about that yet. Pretty soon you'll be able to tackle this exact kind of problem where we don't ignore that, but in this case we're going to just because we haven't learned the tools of how to deal with it. So the first question I asked you to figure out is the angular acceleration of the ball. So again, what we have here is a situation where we have a ramp, and we're going to have a ball. His ball actually happens to be red, the little treat ball that has the treats inside of it. They're not red, but they are in this picture. And it's going to roll down the hill. So it's going to go and it's going to sort of roll down as it goes. And there's various different things I asked you to solve for and various different things that you're going to be able to determine in this problem. So first thing I ask you to find is the angular acceleration, alpha, right? That's alpha, okay? So we know that tangential acceleration is equal to alpha times r, where tangential acceleration is the acceleration in a linear manner of any point on the edge of the ball. But what we've learned is that the tangential acceleration also corresponds to the exact same as the forward linear acceleration of an object if it's rolling without slipping, as we have here. So the acceleration down the ramp is going to be the tangential acceleration of the ball. Now, what acceleration is that? Well, we know that the ball is being pulled by gravity. So like if we were to do a free body diagram, we'd have gravity pulling it down and the normal force perpendicular to that. And what we could find, and you could actually prove this using conservation of energy and so on, but that the thing causing it to accelerate down the ramp is really just the x component of the weight force. So if we made a little triangle like we sometimes do out of the weight force where we have wy down and wx horizontal, we could find that wx is the only thing causing it to accelerate, which is mg sine theta. And since we know force, sum of the forces equals ma, then what we have is that mg sine theta is just equal to ma, and so the acceleration down the ramp, and when I'm calling this the x direction, right, this is ax, I'm dealing with rotated axes, so I'm defining x as down the ramp in this direction and y is perpendicular. And so in that situation, what we have then is that our acceleration is just going to be equal to g times the sine of the angle. So our tangential acceleration, which is the same as the linear acceleration down the ramp, is g sine theta. So when you go to solve for alpha, you can say g sine theta equals alpha multiplied by r, or alpha equals g sine theta over r. So now you have the linear acceleration of Gus's ball down the ramp and alpha. I think I'm going to stop here in the hint video because now I'm guessing that you should be able to go through and solve for the rest of these using a combination of kinematic equations and other ideas that we've talked about. Maybe I'll just give you one more hint just because, you know, I'm so excited to be doing physics this morning, that on B, we have a situation where an object starts from rest, so V initial is 0. V at the bottom of the ramp is what we're trying to find, and now we know that our acceleration is g sine theta, we have a number for that, and our distance, our delta x, or x minus x initial, is going to be equal to the 8.5 meters. And so we should be able to use the equation of motion, v final squared equals v initial squared plus 2a x minus x initial, because we're defining where it starts at the top of the ramp, x initial, as the 0 meter mark. So we can solve this to solve for v, and once again, just like we had this equation with our acceleration down the ramp in tangential, we know that v tangential, which is the same as the velocity of our object down the ramp, is going to be equal to omega multiplied by the radius of the ball. And so right there, you can solve for all of these, and I bet you can use kinematics and your understanding of motion to even solve for D and E as well. In fact, you could have done D without any of this help video just by knowing the length of the ramp. So anyway, I'm going to stop there and let you guys do the rest. Let me know if you have any questions, and have yourselves a box-worthy weekend.